My name is Andrew Gross, and I am the Simulation Product Specialist here at GoEngineer. And yeah, go ahead and sit tight, and hopefully you guys enjoy the webinar and you guys get something good from it. Okay. So we all recognize this, right? It's a blender, something that most of us have in our kitchen, right? We use it for all sorts of things. So one thing we know about a blender, well, it has all these buttons, right? But most of us, we buy a blender, it's got, say, these 15 different types of choices, crumb and blend and puree and, all these different choices. But most of us, well, we really only know two buttons, right? We know blend and we know off. But what about all these other buttons? What are they used for? Well, I'm using that kind of as an analogy for flow simulation. Flow simulation is, it's a really broad spectrum CFD tool. It does a lot of stuff. But what we notice is that often there's maybe just a couple things that people know how to use, whereas we have all these other choices, different types of radiation, compressible and incompressible fluids, non-Newtonian fluids, rotating reference frames, all sorts of things that a lot of people never really had the time to explore. So this webinar, we're really going to talk about, or mostly we're going to talk about, some of the techniques and capabilities that are not used very often but are extremely powerful. So the first thing we're going to take a look at is something called a particle study. And we'll get into this pretty deep, and you'll show really the power of this, where we can include real particles in their behavior. And then we're going to go on and take a look at rotating reference frames. And this is a technique used to analyze things like fan blades and impellers and parts that are rotating in usage, but you'll see how our approach and how we tackle those types of problems. And then we're going to go on to a parametric analysis, which is an optimization study, and it's going to be optimization based on shape optimization, geometry. Okay, so like I said, we're going to start off with a particle study. So let's talk about the problem description, and then we'll jump into SolidWorks Flow Simulation and show how we tackle it. So take a look at the problem description. Say you have a vacuum system, and this is used to remove iron filings from, say, a mill. And this is what we're really modeling here is a hopper. So it's inserted into to gravitationally separate out iron filings before it hits the filter stage, right? So if all of these iron filings hit the filter, we just plug the filter. So this is really used like a settling tank. Okay. So how are we going to handle this problem? Well, firstly, we're going to use a particle study and flow simulation to analyze the problems. So I'm just checking on a question. Okay, sorry, thanks guys. Okay, so we're going to use the approach. We're going to use particle study and flow simulation to analyze a problem, and we're going to determine, well, we have control of, say, the fan speed of the blower system, and we want to ensure that the iron filings don't hit the filter stage, that, say, we want all of them to settle in the settling tank before they hit the filter. And as far as the analysis goal goes, we're going to say that all the iron filings, our goal is that all of them settle in the settling tank and essentially none of them escape. Okay? So from here, let's go ahead and just go right into SolidWorks. So here is the hopper system. And let me just take the transparency off here so we can kind of look through it. It's just essentially a tank with an input pipe and an output. It's very, very simple. I'll do a split view just in case you can see, it's hollow on the inside. That's the outlet, and here's the inlet. Very, very simple study for flow simulation, but we'll show you, we're going to go into these advanced techniques and use particle study to analyze, the iron filings and actually really model them. So I assume most people on this webinar have at least used flow simulation once or twice, so we're going to start with understanding a little bit about the analysis, and we're just going to start off just by using the wizard, which is what we tend to use to start a study. Wizard's a great place to start. It helps get our foot in the door for creating new projects. So let's just call this one, let's just say that we're going to start off looking at, say, the incoming air, the air with the iron filings, is set at about 60 feet per second. We know the velocity of the air. Of course, we can adjust that, but let's just call this 60 feet per second. And we know that 60 feet per second is carrying the iron filings. And we have, say we have an anemometer somewhere to measure the wind speed. Okay, we just choose a unit system. This is an internal analysis. And we're not going to use any of these settings here. This is a really very simple analysis. As far as gases go, we're going to say it's just air. And so these are going to be some of our thermodynamic parameters as far as the initial condition goes. And then finally set a beginning mesh setting. All right. So this is our computational domain, this box around. I'm just going to go ahead and hide that. And the first thing I might want to do, well, I want to change the transparency of everything so I can kind of see through a couple things. Next, we want to apply some boundary conditions. So we know on the outlet over here, just going to go ahead and use select other and just go ahead and grab that boundary condition here. And we're going to say that this is just going to be a static pressure, just ambient static pressure it's blowing out into. Okay, and this is sort of another boundary condition. Go ahead and choose the inlet. And like we said, we know there's going to be an inlet velocity, and we want to start at 60 feet per second. Okay, so we've set our boundary conditions. And under goals, let's just go ahead and set a global goal for maximum velocity. We're really interested in maximum velocity of air going through the system. And from here, we're going to go ahead and run it. I'm going to run this live because it actually runs very, very quick. And we can take a look at the monitor and watch how kind of fast it takes, fast it solves. Okay, so I'm going to bring the monitor over. Okay, capturing the mesh. While we're here, let me make sure that there's, see if there's any questions. We're going to try to keep questions to the end, but if people have questions during it, I'll periodically go back and take a look and see if anyone has asked any questions. Sometimes we'll be solving a couple things and see if I can answer some questions along the way. Okay, so this thing's solved very quickly, right? Maximum velocity is about 94 feet per second. That's within the internals here. Close out. Now let's take a look at some flow trajectories. It's a good place to start. See the behavior of the air as it's passing through the hopper. We'll choose the outlet as where we want to start all of our flow trajectories. Say we want to see 50 of them. The arrows here of velocity. All right, let's take a look at that. All right, so this is the behavior of the air as it's passing through the hopper. Okay, right? A lot of activity taking place here. So this tells us what the air is doing, but this isn't really giving us an idea about, say, if there were iron filings or some sort of particles in the flow. It's not telling us the behavior of that. This is just giving us the behavior of the air. So let's start the particle study. Particle study is really great. It is what we call a post-process technique, where after we run the flow analysis, we go back and in the post-process side, we run the particle study. Go ahead and hide this. So now we'll start the particle study. And you'll see how really easy it is to set something like this up. So we right-click particle studies. That's in my tree here. And I'm going to use the wizard like I've used to create the analysis. And let's call the name. We'll call this iron filings. Okay, so the first thing it's going to ask us is, well, where are the iron filings coming from? Well, we know they're coming from the inlet. So let's go ahead and just select this inner surface. Okay, we know they're coming from there. And this next call out is, well, how many number of points? So that's really, we're going to analyze essentially how many particles are we going to be looking at for the analysis. So let's look at 50 particles. And here it's going to say, well, what's the diameter of the particles? Well, they're really small. Let's say they're 0.05 millimeters. So really, really, really small bits, right? Something that's going to really want to escape. So we know that's the size. And now we want to choose, well, what are the particles made out of? Well, we know they're made out of iron. So we have choices for, say, liquids and solids. Let's choose solids. And now we'll go iron. And now we want to choose the mass flow rate. Well, how much stuff is really pumping through here? Well, this is actually a pretty large hopper, if you can see the size. This is about 10 feet tall. The thing's pretty big. And we're saying on average, it's getting about 1/4 of a pound of iron per second. So lots being driven through here. And of course, we have the choice to initial particle study. We just want or initial particle velocity, and we just want that to be relative to whatever flow condition it's in. But we can also choose an absolute particle velocity. Say that the particles have their own velocity that is separate from the flow condition. All right, so let's go ahead and hit next. And now it's going to ask us for some other questions. Well, accretion, so we want to turn that on because we're assuming that at the bottom of the hopper, that's really where it's going to, that's where our iron filings are going to basically be stuck to the inside and not going to want to escape. So we want to turn accretion on. We could choose erosion, but we know that we're not interested in that. But we are definitely interested in gravity. So we can see that right now it's set in the y direction, global y direction and minus y direction. And gravity is really going to help dictate kind of the behavior of these iron filings. And now we can even choose, we can get down to the granular level, right? Well, what's going to happen when a particle contacts a surface? Well, is it going to be absorbed? Like that would be the case of, say, something like small water droplets may be absorbed into a surface, or if it's wood or something like that. We can also choose an ideal reflection, which means that it's going to, the initial velocity before and after the initial and final velocity after an impact is going to be the same. We can also even get to the point where we're choosing a coefficient of restitution for every collision. Now, we don't need to go that deep. We'll just use an ideal reflection for this one. It's fine. And we're going to be looking at trajectories and statistics both. And now we go ahead and run it. So this takes about 30 seconds to run the particle study. Let me go ahead and check for any questions. Okay, no questions yet. Okay, our particle study is finished. And now you see in our particle studies we have, a tree that's where we've defined all the conditions. Well, let's go ahead and take a look at, let's go ahead and play the animation. All right, so let me zoom in here and I'll give it a sec for you guys to look at. But this is modeling now the part of these iron filings coming in through the input. Some of them are settling, but we can see that obviously many of them are escaping through the output, right? That's not that good. We know that we want to try and have 0 on the output. So we know that some are actually escaping. Well, next I'm going to show you actually the technique we use to analyze, well, how much is escaping, okay? So if you remember, we assumed 50 particles were entering, right, at a certain rate. So we can do in post-processing, we can choose what's called a surface parameter. And I can choose the outlet surface. You can also do that by picking the boundary condition. Okay. And you'll see that we can find a result here for number of particles. So this is going to calculate how many particles are escaping. So I hit show, okay, and the number of particles escaping are 13, right? So we know that we started with 50, but 13 are leaving. So essentially we can say that 26% of the particles that are entering the system are leaving the system. That's not good enough. We want that to be as close to 0 as possible. So what kinds of things can we adjust at this point? Well, we can adjust that in the input speed, the fan speed, right? We know that we did an analysis this time at 60 feet per second. Well, you can see here I have a bunch of different studies I've created at 50 feet, 40, and 35 feet per second. So I've already ran these and ran the particle study. So let's go ahead and take a look at, so we'll go ahead and run these. Whoops. Let's take a look at what these particle studies yielded. Okay, takes just a moment. Okay, sorry about the dead air. I'm just letting this thing run. Okay, so we don't have to really, we can take a look at the You can play it and see what's happening here. So at 50 feet per second, well, we can see that there are fewer particles leaving, but there still are particles leaving at 50 feet per second. So when we post-process, we'll look at the surface parameter. Well, we're at 15. So again, that's still more than 0. So let's go back to the PowerPoint and take a look at some results. So what we found is that at 60 feet per second, we saw 13 particles escaping the hopper, which equated to 26% of particles escaping. At 50 feet, we didn't see a very big difference. In fact, just from 26 to 24%. But as we reduced that speed of the flow speed and went down to 35 feet per second, well, we're actually able to get 0. Let's go back and take a look at that analysis. So at 35, at 35 feet per second, we were now able to see nothing leaving the hopper. So you know when you're running this on the bench or actually in service, we know that 35 feet per second based on the particle size is going to be kind of that butter zone to make sure that none of the particles escape and they all settle in the hopper, and we essentially have pretty clean air coming out the outlet before it hits the filter. Okay. So that's our particle study. And next up, let's take a look. We're going to change gears a couple times. So next, let's take a look at rotating reference frames. So let's take a look at this problem description. So it's an RC helicopter that we're designing, and we're wanting to build this. And we want to run some analysis on what we think is, at this point, the final design, the final revision. Okay, so or a revision's about to be put out. So what we really want to know is determine, well, what's the RPM required to achieve the appropriate thrust for the RC helicopter, right? You'd be amazed that we can run that type of analysis in flow simulation. We can determine thrust. So we're going to use rotating reference frames to simulate the effect of the blades turning and generating thrust. And the goal of the analysis, well, we want the acceleration of the helicopter to be around 3 meters per second squared at full thrust. So that's really what we're looking for there based on the RPM. So let's take a look at this analysis. Okay, so here we have our RC helicopter. And just like in the past, we're going to start off just by using the wizard, just by creating a new analysis from scratch. Now this one we're not going to run in real time because it takes a little bit of time to run. Let's just call this, we'll just call this thrust, because that's really what we're looking for here is the thrust. And we'll choose a unit system. It's going to be an external analysis. But what we want to make sure to check here is the rotation. And we're going to choose some local regions as the rotating reference frames. Just use an air for now. Okay. And we set some initial conditions and some initial mesh settings. So let's go ahead and let it build the analysis in flow simulation. Okay, so the analysis has been built. And you can see it's got a very large, let me turn perspective off here. Sorry, guys. That's a little confusing. All right. So you can see it's a really large computational domain. Let's go ahead and just shrink that a little. We don't need it to be this big. This will make things run a lot faster. So it's very easy to change the computational domain to kind of fit the project we're looking at. And now I'll go ahead and hide it because we don't even need to see it really. Okay. Check on questions. Okay. So now let's go ahead and build the rotating regions. And you'll see how I've done this. So in the feature manager, when I choose the modeler, actually look at the assembly, see there's a couple parts that I created that I've just hidden for now. I'm going to go ahead and show them. But you can see that I've created these disks. This is just standard parts, just these disk parts. And I've created these disks to go right over the blades. And this is where we're going to define as a rotating region. We're essentially going to spin air around the blades to simulate the effect of the blades actually spinning on the helicopter. Okay, so we're going to go to component control. We're going to knock a couple of these components out because maybe we don't need to look at all of these components. Okay, just to make our analysis a little simpler. And now let's go ahead and define the rotating regions. So we do this by right-clicking rotating region, simply choosing this modeled part and giving it a certain rotational velocity. So let's say we start off at 3,000 RPM. And you see that I can dial in RPM even though it's set at radians per second. It's going to convert it for me. That's pretty nice. And let's go ahead and include our second rotating region. Okay. Now what I failed to, oh, not 3,000 radians a second, sorry. What I forgot to mention is that these blades actually spin in opposite directions. So if we look at the pitch of the blade, we can see that these blades are mirror opposites of one another. So that's the way that actually this RC helicopter remains stable, is by the two blades rotating in opposite directions. We can even simulate that. So our real endgame goal, though, is we want to determine what type of thrust the blades are going to produce. So let's go ahead and hide these rotating regions just so we don't have to see them. Okay. And let's create some surface goals. So what we're going to do is we're going to choose all of the outer portions of the blades, both top and bottom. And we want to create a separate goal for each blade face. And what we really want to solve for is going to be force in the y direction, right? That's going to be the force, the lifting force or the thrust. So we can create a goal for that. Let's go ahead and create all these goals. So create 8 of them, 1 for each side, 4 for the top, 4 for the bottom. And at this point, we can go ahead and actually run this analysis. It's that simple. So I've ran it. So I'm going to go ahead and change my configuration. But instead of having a different goal for each face, what I've done here is I've actually only created 2 goals. One for all of the faces of the top blade, one for all the faces of the bottom blade, so they can all add up together. And I can determine what the global thrust is based on that. So I'll go ahead and load these results. And the first thing we might want to see is a cut plot. So new for SOLIDWORKS 2013 is the ability to, or sorry, this was, I guess, in 2013, we have this new thing that's called streamlines. So in a standard cut plot, we can get a really good view of kind of flow trajectory information that's painted right on the cut plot. It's really great. They're being calculated directly on my video card in real time. So as I zoom in, you can see I get more definition as I zoom in. Definition goes away as I zoom out. It's really kind of a great way to post-process a cut plot. So we can see the direction of air flowing as it's passing over both blades. Okay. Next, you might want to take a look at some flow trajectories. So it's creating flow trajectories right now. Okay, and let's go ahead and play them. So I'm not sure how the video looks, how this animation looks on your end, but you should be able to see that we can view and watch as air is being drawn in, creating some vortices down here and generating lift. So this is all being controlled by the 2 rotating regions spinning around those blades. That's what's developing this thrust. So the next thing we might want to do is really look at what we call a goal plot to kind of see, well, how much thrust was generated. So if we open up a goal plot, we can hit show, and under our goals, well, we can see that the top rotor system created 0.083 newtons of thrust, and the bottom rotor system 0.028. Maybe this is a result we didn't know was going to happen, that the top rotor system is going to develop quite a bit more thrust than the bottom. Okay. So let's go back to the, let me just make sure there's no questions. Okay, great. And let's go back to the PowerPoint and take a look at some results here. Okay, so we can see that when the angular velocity of the blades was 3,000 RPM, and we know the mass of the helicopter, 0.034 kilograms, and we calculated the thrust of the top rotor plus the bottom rotor, which is a total of 0.112 newtons. And, you know, from physics, Newton's second law, right? We know that force equals mass times acceleration. We can rewrite that as acceleration equals force over mass. And we can determine that the acceleration at 3,000 RPM is 3.22 meters per second, which is very close to our goal of 3 meters a second. So we've solved this problem. It's great. It may have taken a couple chances. Say in real life, it may have taken a couple tries or a couple different RPMs, but until you get the acceleration you want. But this can go a long ways before you have to prototype and actually build something and test it on the bench. It's a very powerful tool. Okay. So we've taken a look at rotating reference frames. And now our last study we'll be looking at this afternoon is going to be a parametric analysis or an optimization. So the part we're looking at here, again, we're changing gears, we keep changing gears. But so the description of this problem is that this is a catalytic converter, right? So we know that catalytic converters have very expensive metal that are used to make a catalytic converter. And one of the goals of creating a really good catalytic converter is that you're really normalizing the airflow over all parts of the converter. So you're not getting, say, one side of it getting more airflow than the other, because you know that it'll burn out one side versus the other, and then you essentially have to replace it before all of those very precious metals are utilized within the catalytic converter. Very expensive. So you want to really normalize that flow to maximize the lifespan. So as far as the approach goes, we're going to use a parametric analysis to optimize the geometry for maximum efficiency of the system. And as a goal, we want to find a uniform flow rate through the catalytic converter. Okay, so let's go back to SOLIDWORKS again. And let's open up our catalytic converter analysis. All right, so here's our catalytic converter. And let's take a look at our initial design. Okay, so let's take a quick, just explain what's going on here. So we have an input here in the velocity of 12 meters a second. And over here we just have a static pressure. So our airflow is coming through the pipe, through the the catalytic converter block, just one big block, which we used our porous medium tool in SOLIDWORKS Flow Simulation to determine that. And we're saying that it's unidirectional, right? So it's not going to be, it's not omnidirectional, it's unidirectional. And some goals that we've created are looking at flow rates on these two faces. Now this is something of particular importance I want to explain here. So I created this simple piece of geometry in SOLIDWORKS, this guy here, this I'm calling a sensor. And it's just a little disc or a slotted shaped disc that I've stuck in right inside the filter, and I've used a split line to turn into two different faces. So why did I do that? It looks like it's just blocking the flow at this point. Well, by using component control, what I'm able to do is I'm able to disable this sensor part from my component control. So I disable it. So as far as flow simulation goes, it doesn't see it. It's going to blow air right through it. But the benefit of that is I can create a goal where I can look at the flow rate, this independent flow rate on either side, on the left side or the right side. So what's that going to do for me here? Well, that's going to let me know if one side is going to get utilized more than the other. That's how I'm really going to analyze the lifespan of this catalytic converter, is if the flow rate's more on one side than the other, then that side's going to get used up quicker, which means the whole thing is used up much faster. So that's what I've done, is I've created a goal for flow rate on one side and the other side, and a simple equation goal where I've divided that flow rate of the left side divided by the right side. So in a perfect world, if this thing were to be utilized and if evenly, an optimized flow path with this value, this equation goal would be equal to 1, right? You get the same flow rate from the left side and the right side. So our initial design, let's go take a quick look at flow trajectories. We'll just kind of hit play here and we can see what's going on. Well, we can quickly see just from looking at these flow trajectories. Whoops. Sorry guys, I don't want to get dizzy flipping this thing around here. Oh, well, not playing with me. Not playing nice now right now, but well, we can see that this flow, it's really using this bottom portion. There's much more flow on the bottom portion here than the top. So this isn't really going, the lifespan of this is going to be not very great, right? Once the bottom half is used up, the top still has nice, fresh catalytic converter material, but it's going to get used up quickly. So we can post-process and determine that value of, how inefficient it is. So under a goal plot, again, we can look at our goals of, the left side and the right side. If I show here, well, we can see that the flow rate on the right side is 0.0024 meters per second, cubic meters a second. But on the left side, it's 0.0034 cubic meters a second, yielding my equation goal equal 0.69, which means that really we're only utilizing 70% of the catalytic converter right now, right? So when this thing's completely gone, really we're assuming about 30% of this catalytic converter is still going to be fresh. It's just not utilized because the geometry is incorrect. So how do we change that? Say we're really stuck to the shape, there's nothing really we can do here. So when I go back to the modeler, well, I added some baffles on this internal of the pipe. You can see what I've done here, right? See these little parallel little baffles, and it's going to help direct the incoming air, and we can change the angle of these baffles as they approach the catalytic converter. Okay? So we're really hoping this helps. But what we're going to do is we don't really know what that angle should be, right? So when I look at the sketch we used to create this, these baffles, I used a pattern to create them, but we can see that from this line, I chose a degree of 130 degrees was where I wanted to start out. But I have no idea really what angle is going to optimize or maximize the flow rate between the two different surfaces. So what I've done is I created an optimization analysis to help with this. Really, what's the heavy lifting of this of this whole entire process? Well, what's the angle here? So let's take a look. Under Solve, we have a choice for a parametric study. So what we can do here is let's go ahead and set up the parametric study. This is how you would set this up if this is being your problem. I'm just going to move this around a little bit. So we want to create a goal optimization. And this is going to be based on a range. So when I click here, I've already selected the sketch. Well, let me just go ahead and start from scratch. Say I were to delete that. So the first things we can choose for a parametric study is we can choose to add a dimension parameter, which is what we're going to do here, or we can add a simulation parameter, something like a flow rate to be optimized. So in this case, we're just going to choose, we want to choose a dimension. So going into the modeler again, I can go ahead and pick that dimension from that sketch. This 130-degree sketch. I know that that's what I want to change. And I want to create a range saying from 50 degrees through 130. So we're at the maximum now, but we can change that. There's an 80-degree change here from 50 to 130. We don't know where that perfect location is in that range. But flow simulation is going to give us that information. Okay. So as far as output parameters, well, what do we want to be based on? How do we know which iteration is going to be better than a different, which one's going to be the best? So, I'll delete that again. So we want this to be based on a goal. Okay? And we're going to use that equation goal. Remember when we said that equation goal is just dividing one of these sides by the other, flow rate. So we really want that value to be as close to 1 as possible. Okay, so based on that equation goal, we want to see our target value to be 1. Now under here, this is our deviation. So how much tolerance do we have? So I'll give it 0.01. That means that when that goal equals 0.99 or 1.01, anywhere in that range, we're going to say that we're good. We're going to say that's close enough. And now under scenario, well, I've already ran this one, so we can see what ran. But we can see that what happened is it created these 5 different design points. We started at 130 degrees, so the maximum. And then it went to design point 2, which is 50 degrees, the minimum. And now it uses something called the secant method to zero in on this perfect, the perfect angle to maximize my goal. And what we can see here is that 71.15 degrees of that angle gave me an equation goal of 0.9932. Right? Our target is 1, we know that. Our discrepancy is below 0.01, so we know that this finished. And this is where, we know that our goal had been reached. So let's go back and take a look at the results. So first, let's just go ahead and click through the different configurations that it created. So Flow Simulation created these configurations, these different design points. So let's take a look at our initial design. Oops. Sorry, when we add our baffles in there. So that was the first at 130. And next take a look. Well, now see, you can see here that they've changed to completely rotate in the opposite direction. This is the 50 degree. And as it got closer and further down the road, you can see that the changes got more slight and much more optimized until we actually hit that design point of 71.15 degrees. So let's take a quick look at these flow trajectories. And we'll be able to see right off the bat a huge difference, right? Compared to the previous flow trajectory we saw, where everything was so heavily based on the bottom, now we can see that it's much more even passing through the catalytic converter, which, what does that really equate to in real terms? Well, that equates to actually having a longer lifespan, right? This is a better product. And we use flow simulation to basically target that perfect angle for this type of analysis. Okay. So just in case you weren't able to see on the bottom of the parametric analysis after it had ran, I wanted to give a kind of a detailed view of that, just kind of zoom in to kind of show that how it went through the different design points starting at these degrees and going to 71 degrees, which is the optimum, and kind of giving some information about the target value, the discrepancy, and the actual equation goal. Okay, so we saw that at 130 degrees, the efficiency was about 76%, so not so good. And then at the very opposite end of the spectrum, where we had it at minimum at 50, the efficiency was actually better, but it still wasn't very good, 86%. And we can see that the optimized result of 71.14, that the efficiency was up to 99.6%. So this is really kind of the telltale to everything. So now that we've looked at parametric analysis, well, let's take a look, let's kind of recap what we've seen here today. So we're able to simulate the particle behavior in that first analysis with the hopper, we could take a look at those iron filings and change the velocity of the input velocity until we made sure those iron filings weren't escaping the hopper. That was a really good use of the particle study analysis, which is very powerful. In rotating reference frames, we can actually model rotating regions without having to move a model, which is really nice. And in this case, we were able to look to find out how much thrust was going to come from the RC helicopter. And finally, what we just saw was what we call that simulation-driven design or simulation-driven geometry. And we were able to optimize the design of those baffles to maximize the lifespan of that catalytic converter. So now we go back to the blender analogy at the beginning, right? So we knew how the off button and we knew the blend button. But as we use the blender, we start learning what some of these other buttons are good for. Say this one's good for soup, or that one's for salad dressing, or milkshake, or peanut butter, making a smoothie, pancake batter. So as we explore the tool, we're able to determine different techniques that can be used for different types of analyses. Now going back to the flow simulation analysis. So there's lots of capability within this CFD tool, and it just takes time to learn how to learn and kind of toy around with the tool to basically maximize the utilization of the analysis tool. So that's the end of the presentation. Wondering if you guys had any questions. You guys can go ahead and type them in. I'd be happy to answer any questions for you guys. Okay, so I have a question that someone asked, where did it output the optimum angle? It's a good question. Let's go back to the analysis again. So from that optimization study, we can see that this is the output angle, right? This is where it says the design D2 at sketch 16. So this is our design point. So this is where we can post-process and determine what that output angle is. In this case, it's 71.149. But we can also see that that actual value is now within the configuration itself. So when I open up the part and take a look at that sketch, well, we can see that that sketch, this is real geometry. So it's 71.15 right there. Hope that answered your question. Thanks for asking. And there's another question, will the slide deck be available for download? Unfortunately, the slide deck is not going to be available for download, but we will on our website. We will, probably a day or so, we'll have a recording of the entire webinar. Will be posted. Okay. Any other questions? Okay, looks like there's no more questions. I really appreciate your time, everybody. And thanks a lot. Much appreciated. Once again, my name is Andrew Gross. I work at GoEngineer. This is my email address, andrew.gross@goengineer.com. Let me know if you guys have any further questions. And thanks a lot. Have a great day, everybody.